Good evening, one and all. So, thanks for coming to the webinar. Today evening, I think we'll have an enlightening session wherein we are going to deep discuss for the innovative solutions in the emerging fields of LIB recycling and microelectronics, focusing more on the resource recovery part. I am Jansi from the New Technology and Innovation team of Murugappa Water Technology and Solutions. We are a part of the Murugappa Group. Along with me, I've got Mr. Cameron Lippert, who's the Chief Information Officer and co-founder of ElectraMet, with more than 15 plus years of, industrial and academic research in metal recovery and research recovery in fields of electroplating, microelectronics, and semicon. So we'll move on into the presentation. So Murugappa Water Technology and Solutions is a part of the Southern Indian group Murugappa. We are a part of the conglomerate, one of the 29 companies. So the group by itself is very diversified in nature. So you can see that from metals, from agrochemicals, sugar, bicycles, the services and nutraceuticals. We are there in the we form the sustainability and water management phase of the group. Uh, it is spread across the globe with more than 60,000 employees. We at Murugappa Water Technology and Solutions are an total sustainability and water management solutions provider in the space of water management for more than 4 decades now. I think we are close to around 500 plus assignments completed successfully. With we operate under four major pillars or the business verticals, I would say, to provide the services. They are the automation. We're there in the complete digitization and automation of your plants. We are there with helping the industry with our chemical solutions. I would say it is rather than a product, it's more of an assistive chemical solution. We are there providing the engineering as a total EPC contractors, and we are also there in the service segment providing the comprehensive operation and maintenance for the plants which we deliver, as well as the plants which are already there. We do the plant health audit, and we can deliver you a complete operation and maintenance platform. So that is about MWTS. So coming to ElectraMet is an innovative solutions provider in the field of resource recovery. The focus here is on recovering resources of economical value from the tougher, effluents or the wastewaters, like from your, battery drainage, your mining and metals, your microelectronics and electroplating industries, wherein there is a stress in terms of the compliance, and there is a need of the hour is on the how efficiently we recover the rare metals or the metals of economic interest. So ElectraMet is different from other resource recovery, as you could understand while Mr. Cameron will explain on the differences. How does it differ from the other technologies out there? So basically, from US, ElectraMet and MWTS have taken up a joint solution delivery for the Indian market. Uh, why in India? Because we could see, with respect to these two industries, they are emerging first, and the industries like when the industries grow up, obviously the need for water also moves up. So there is an regulatory norms over there. There is an water stress, and what is more positive is that there is a secondary market. If people there at market can understand there is a secondary or auxiliary market that is getting developed for using the recovered resources from the waste, which otherwise will go unnoticed, and it will also post a challenge of managing them as hazardous waste, wherein there is always a technology, or there is always a thought behind to recover those valuable metals rather than creating a threat out of it. So we could see from various marketing insights that definitely India is picking up in terms of the semicon industries, being the fab, production or the ATP facilities, and we could see more maturity gaining in terms of the EV segments and the associated battery production, and not leaving the tag end the battery recycling. So there is a maturity, or the market is getting more matured in terms of the battery recycling. We could see, when we interacted, we could see there are more structured processes that are being set up. Probably there are more expansions that are going on the in the microelectronics and battery recycling space. As we grow in the EV space, probably around next 3 or 4 years, we'll have to face this challenge of recycling all the end of life batteries from the various vehicles we put on road this year and next year. So the focus towards India is more because while we currently map the global supply chain, the present scenario is that there is an intensity, or we don't see much diversification in terms of supply chain, because we as an technology providers or the resource availability, there is an density in particle geography, and we could see this trend slowly getting diversified towards India and other Asian countries as well. So we could see India gaining more momentum because of this current situation, and people either want to become, uh, independent, or I would say, like in terms of Atmanirbhar, or they want to create or have an multiple choices for the supply chain to go around smoothly without any interruption. With this note, I hand over the deck to Cameron to take us through the application of ElectraMet across both the industries, touching upon the semiconductor as well as the battery recycling. Maybe he'll start with the general flow application, where it describes on where ElectraMet is getting pitched in. Over to you, Cameron.
Thank you, Janshi. Yeah, so when we're looking at wastewater in the industry, every facility seems to think they are unique in their water, but if you take a high-level view, every wastewater application has the same general process. You have the target constituent you need to remove, and then you have pre-treatments to get the water to a suitable state that you can process that impurity you need to remove. Then you have the post-treatment, which is typically the final polishing steps you need to meet discharge compliance. Usually some sort of pH adjustment step to neutralize acid or acidify caustic. And if you look at really every industrial facility, especially in these two industries, you see the same steps repeated again and again. Usually solids, then your target metal, and then acidification. And so take a little bit deeper look at sort of the specifics of the semicon markets versus the black mass refining, the battery recycling process. There's always going to be a solids handling issue. Then you're going to have some sort of general purification to get the water to spec, target metal removal, and then it's in the final kind of polishing step. So in this webinar, we're going to start with the semicon process and then finish up with the battery recycling. And we're looking at the semiconductor market. Not only do you need to meet discharge compliance for environmental regulations, there's now growing pressure to do it sustainably, to use less water or recover water, and to send less waste to landfill. And current incumbent solutions really struggle to kind of do all of this. The good at meeting compliance, but not so much with the rest of these ESG recovery targets. Next slide, please. And this is because there are a variety of different types of wastewater in the semicon site that are very, very different. And the incumbent solutions are designed to treat one but not the other. And so the net result is an inefficient process that is really unsustainable. And the two main sources are shown here. The copper CMP is the chemical mechanical planarization process. This is where they polish down the wafer to make it nice and smooth for the chip manufacturing. This is typically processed in-house for wastewater, and it uses probably 30 to 40% of the total water in a fab facility. And then on the extreme side, you have these wet etches. So these more bulk removal processing, it tends to be much, much higher concentration, but lower volume. And they also contain a lot of hydrogen peroxide. So the combination of hydrogen peroxide plus the high concentrations of the metals makes it very challenging to treat on site. And so they typically just truck it off. So now there's very expensive trucking costs and very unsustainable environmental impacts from the trucking process. And the reasons why these waters are so difficult to treat is because there's a lot of stuff in there. If you have pretty clean water with one target constituent, it's pretty easy. For the CMP on the left here, the target is the copper. But you have a lot of hydrogen peroxide in there, solids, organics, and these all tend to negatively impact standard treatment solutions. On the right, you just have a significant amount of copper. That makes solutions like ion exchange chemicals very expensive to process it. So importantly, you have just large amounts of unknown chemicals. So this combination makes it challenging, right? I said, the current incumbent processes have been designed to meet discharge compliance, not necessarily do it sustainably, right? They work very well when that was the only option, right? We now have new options. So if you want to do discharge compliance, meet environmental regulation, also do it sustainably, we need new innovative solutions. And then you're looking at, what is the right tool for the right water quality? And this is where the existing solutions are suffering. You can see here in the green on exchange, that's very good for the CMP waste, but doesn't work for the concentrate stream. And you look at the electrowinning, it can process part of the concentrate, but it can't get down to discharge compliance. And there's a huge gap in the middle here around that 1,000 ppm range where there's really no viable economic solution. And that is why they tend to truck off that concentrate instead of processing it down to discharge compliance. Because either way, you have to do some ineffective, unsustainable, high-cost solution to cover that gap. And ElectraMet has solved this problem by using electrochemistry and developing a series of reactors that can process the entire concentration range in a single skid. So whether you're starting in the lower ppms that you see in CMP, or you're starting at the high concentrations that you see in the wet etch processing, our solutions can then process it all the way down to environmental compliance and discharge regulations, while also recovering that copper as a value add and not sending waste to landfill. Next slide, please. And we've been able to do this by taking the lessons learned from electrowinning, taking those core concepts of how to plate metals and modify the reactor design to make it more efficient at lower concentrations and make it more selective. So we use a porous carbon cloth cathode, you can see in the picture there, and that is where the water is flowing through. So now you have a lot of high water electrode contact area, which overcomes mass transfer limitations, and that allows you to hit the lower concentrations in the effluent. So we put this in a complete system You can go next slide. So putting this complete process flow for the wastewater at a fab facility is you still got to handle the solids and the peroxide because they can negatively impact the electrochemical treatment. But the key benefit over electrochemistry versus ion exchange is if there is residual peroxide, it will not destroy our media. Hydrogen peroxide will decompose ion exchange resin. If hydrogen peroxide enters our system, it's just a modest inefficiency that creates. So we'll use the energy to break down peroxide instead of remove copper. So through a combined process, we can develop a more efficient system. And now the net sort of waste product of our process is a high purity 99.99% pure copper metal. So you can now recover this as a new revenue stream, which helps reduce the total cost of ownership of this process, but also helps you meet ESG goals by not sending any waste to landfill. And more importantly, for every pound of copper that's recovered, that correlates to about 4 to 6 pounds of CO2 that is not emitted because you no longer have to mine that little bit of metal from the virgin ores. Next slide, please. So Josh is going to take a look here on how the really total process flow comes into place from pre-treatment to metal removal to then post-treatment. Over to you, Janshi.
Yes, thanks, Cameron. So, like Cameron was explaining in deep on how the metal gets recovered, for the complete, solution for the wastewater from the battery recycling industry or the semicon, there's going to be a set of pre-treatments to remove the suspended solids because these are typical, as explained, this is a porous carbon cathode. So we don't want the recovery of TSS happening in the cathode and the entire cartridge becoming a particulate filter. So we tend to remove the TSS way high before it enters into the metal recovery unit. And depending upon the metal, there is an effective pH that plays an important role. So depending upon the metal to remove and to what concentrations, there could be adjustments in the pH. And this entire technology can remove peroxide, but that is not the intended goal too, because we are focusing to take off the valuable metals. So we have a more economic solution for the peroxide removal so that it doesn't interfere with the core technology. But the difference is peroxide does not put a detrimental effect as it does to the ion exchange technology. So we can take care the peroxide well before the system. But even if peroxide is there, it is not going to degrade the system, but it is making it less efficient. So we thought we should be knocking off peroxide even before getting into the target metal removal. So once there is a removal, we can create a recovery route so that the metals can be recovered at a greater purity. And post recovery of metals, if we have an enough volume and further treatments to be made, we can and we will be focusing on the recovery of water which is free from metals, because metals are very high high molecular weight contaminants which restrict our water recovery options. So once we are free from these metals, I think we have a free hand to provide an optimal water recovery. And since most of these industries might require an regulatory brine management or a zero liquid discharge, we would be providing more sustainable brine management systems. And the solids that are recovered from the pre-treatment as well as the brine management would be way less in volumes to be handled when compared to the conventional route of handling this wastewater, because we feel in conventional it is more of in direct neutralization. Both these waters predominantly are in a very high acidic range, so the industry tends to neutralize them with more alkalis, and we are left with a very high volume of hazardous sludge. So when compared to that conventional, we will be hitting a very low solids volume that can be managed off at a better operational cost.
And just one thing to add, Janshi, to that
Yes.
process flow sheet, the combination with balance of plant and why this collaboration is so valuable is the removal of the peroxide in the metals will enhance the lifetime of that brine management, those membranes. If you remove those metals, remove the peroxide, you have now the phthalate and scalants are now gone. So the total process is going to be more sustainable, more energy efficient, more cost effective than individually.
Yes.
Next slide, please. And so how does the ElectraMet sort of a simple process work? Is we have a sort of a two-step process. So coming from the feed tank to this blue line, we remove the metals inside of our electrochemical reactor. So we go from the dissolved metal, we plate it out on our cathode. Once the cell is saturated, we have an internal closed loop process. This is very indicative of a clean in place type process. So we use some sort of acidic media, a regeneration solution that collects the metals from our reactor and concentrates them up in this regen tank. That reactor is now available to use again to remove more metals. And once the copper or other metals in the regen tank is high enough in concentration, we can implement a electrowinning type solution to recover these metals in high purity. Right, we now have gone from what is typically a very dilute metal stream to a highly purified concentrate in acid, which is now perfect for electrowinning. And by doing this, we can have a total solution closed loop process to go from metals in the wastewater to a high purity value add product. Next slide. And we have been doing this for almost 3 years now in actual fab facilities. Taking CMP wastewater off of this process has a very dynamic feed concentration, but because we operate using electrochemistry, it can automatically adapt to incoming process concentration changes and still meet their discharge compliance. So for this fab facility, the limit was 2.07 ppm of copper. And you can see over this whole year, and this is data that the facility themselves pulled, not us collecting it, that even though we had a broad range of concentration, sometimes even spiked as high as 100 ppm here, the ElectraMet system was able to self-adapt and modify its operation to always hit compliance. So there's peroxide bleed-throughs didn't negatively impact it. Upstream process changes didn't negatively impact it. So we had consistent and reliable environmental compliance while also recovering the metals. Next slide. And taking on the other side, the extreme side, the wet etch, the electrochemical plating, the higher concentrates, we can now use this combination of our electrochemical reactors to go from very high concentration down to environmental compliance. And we can do this very efficiently in terms of an energy standpoint, but also very efficient in terms of a time and labor standpoint. So on the plot on the left here, we're looking at the voltage you apply over time as the copper is removed from this concentrate. So we're doing this to find what is that optimized concentration process to switch from one reactor to the next, so it's best suited for that operations. And once you get down into the kind of 8,000 ppm range, you start to see the voltage tick up a little bit. And this is happening now because in this reactor, there's a big gap between the anode and cathode. So mass transfer has a challenge. So you have to get that middle molecule from the water to the cathode. in order to overcome this mass transfer, as you get more and more dilute, it takes more and more voltage, more energy to do that. And then looking down here on the right, you can see the current efficiency. So this is how much of the energy you're using is going to move in the copper versus other unwanted parasitic reactions. So as we get down, again, on the darker blue triangles, you see it is very high efficient and it slowly tails off. And once you hit around 1,000, 2,000 ppm, you see a huge drop off in efficiency. So that is the sweet spot of where we want to switch from our core recovery reactor to our mid-range reactor. Next slide, please. And that's what we're showing here. So now we developed this reactor that is in between standard electrowinning and better for bulk than our other polishing reactor. So this handles ranges from 5,000 ppm down to 500 ppm very efficiently. So look at these lines here of coming in from the feeder of about 3,000 ppm. So this is the effluent from an electrowinning reactor. So it takes the copper from whatever 10,000 plus ppm down to 3,000 very efficiently and produces the copper too. We then use our mid-range delta system to take it from 3,000 ppm down to anywhere below 500. And this one we kept going, it's very linear. So that means you have the same efficiency down to about 1 ppm. And in this case, that met discharge compliance. There are all going to be some water matrices where the efficiency will drop off around 500 ppm. In that case, we wouldn't switch to our other reactor. Next slide, please. And so here is an example of one of our small installations showing the small footprint. Because of the high efficiency and the modular nature of this process, it can be very easily retrofitted into existing facilities, or for new builds, it can allow for more room for production facility because it's a small footprint. We don't need a large space to implement this wastewater treatment system. And on the right here, you can see some of the copper pulled out of the tubes. Yeah. And so that's going to conclude the semiconductor portion of the webinar. And now we're going to switch gears a little bit over to lithium-ion battery recycling. And so this has been a very area all across the globe. And if looking at how are these batteries going to be recycled, there's really a few different methods. You can do it directly, direct recycling, which we take the battery cathode material, do a little cleanup process, and put it right back into a battery. You have the hydrometallurgical process, which is you're going to shred the battery, get the black mass from the electrodes, dissolve it in some sort of leaching solution, and then separately isolate all the products you want. This is very similar to what is done in the mining industry. And then the current method that's done today at a large scale is pyrometallurgical. This is where they're taking existing furnaces and refineries and taking the black mass from the shredded batteries and putting it into a smelting-like process. So it works, but it's very energy intensive and very environmentally unfriendly. Most of the new facilities being built are doing a hydrometallurgical process, mainly because of the lower CO2 footprint, lower energy requirements. Next slide, please. And so where ElectraMet can fit in is battery recycling has usually very complicated flow sheets. Removing bulk metals is pretty easy. There's lots of solutions to do bulk recovery. But in the battery recycling process, you need to hit battery grade products. That is a very high level purity that is needed to be achieved. And ElectraMet can bolt on after these bulk removal processes for a more efficient, higher purity products at the end. Next slide, please. And why purity is important is even the smallest bit of impurity in a battery can destroy its performance. It can reduce, next slide, please, reduce lifetime of the battery. Next slide, please. Right, it can reduce the performance, so it won't have many charge cycles. So instead of getting your 200 miles of range, you might get 30 miles of range. If you have these impurities, it can result in unwanted reactions within the battery, and that is a big risk of fire. It doesn't become could a fire happen? It becomes when will the fire happen? So a lot of safety concerns will happen, and there's a lot of increased value in battery grade versus these technical grades because of the high need in these batteries. Next slide, please. And so in the recycling process, there's really 3 pillars you have to hit to have a sustainable and viable operation. You have to have high yields. You have to have good economics, both of your operations, but also of the product you're producing. And you have to have high purities to be battery grade. Hitting 2 out of the 3 of these is very easy. Hitting the 3rd one is near impossible with today's solutions. It can be done on a very small scale, or it can be done on an absolutely massive scale. But most plants will operate in that mid-range where we need new innovative solutions to hit all 3. And all depends. Go ahead.
Yes, the Indian industries are growing with this pyramid. We could see a lot of firms there hitting the MHP and metal salts, growing slightly towards the pre-cam and cam. But as you rightly said, the the evolving towards high purity battery grade materials is more emerging. So it is in the even nascent, but I think we will mature more in that.
Yeah. So it's all dependent on what product you want to make. And what we're seeing today with people in the US, Europe, and some of China is the main focus is get lithium out. That's pretty easy to do by itself. And then make MHP. It's very cheap to make MHP, but there's not a lot of margins. So it is only viable now. It will not be a viable product in the solution. The metal salts, it appears that you have to be very, very large facility processing 100,000 tons a year of black mass to make that really economical, because it's more of a commodity type chemical. So a lot of these mid-range firms are looking to either vertically integrate or partner to make PCAM and CAM directly, just because of the significant value increase. But again, it all comes down to purity. Next slide, please. Right, if you don't have that purity, you can't make your products. You just have a commodity metal, which is now not being competitive in a market versus other ways to get commodity metals. And so what I've done here is pulled a number of specifications from a variety of PCAM, CAM, and battery grade metals products. So you can see copper is a big one, manganese is a big one, and cadmium, right? But there shouldn't be any cadmium in the EV batteries in the first place. We have seen a number of black mass providers that have cadmium in it. And this is most likely coming from people mixing in nickel cadmium batteries. And even one battery in a large recycling plant can produce enough cadmium to be out of specifications. And if you look at down the precursor NMC, so this is the nickel, manganese, cobalt type lithium-ion batteries. These are the cathode materials we're using for these higher value EV cars, these higher ranges. The purity requirements are very strict. And standard hydromet processes used in the mining industry cannot hit these targets, or they cannot hit these targets with meeting the required yields to make a viable economic business. Next slide, please. And so here's going through a little example of, if you have a standard black mass composition shown on the left, what kind of values can you get out of it shown on the right? So on the top right is just showing on a purely same mass basis, what is the value of the different products. And you can see that the CAM is extremely valuable compared to everything else. That is the most valuable product. Right? Battery grade metal salts are also very valuable, but if you only hit tech grade, you're going to lose a lot of value. More importantly here, if you normalize it based on what you can get out in the yield, based on the black mass composition, this bottom right figure shows what kind of operation could you get. And it still shows making CAM is the most value you can do. The metal salts, if they're battery grade, could be very lucrative. The challenge is if you don't get to battery grade and you hit tech grade, that is going to be significant value loss, because the cost to try to get to battery grade is going to be very high. And if you have to reprocess your solution again to get to that final grade, it's going to cost you a lot and ruin your economics. Next slide, please. So looking at the impurity removal, what are the different methods and what are the main impurities? From what we've seen, the biggest impurities that are causing problems is copper and manganese. And how they fit in will depend on what product you're making. So on the bottom left here is a very high-level flow sheet of a process to make different battery salts. So the goal is to make cobalt sulfate battery grade, nickel sulfate battery grade, and a manganese oxide or manganese sulfate battery grade. Once you leach it, there is significant amounts of copper in the black mass coming from the current collectors of these batteries. Now, getting the bulk out is pretty easy. You can add some sodium hydroxides and base to precipitate out iron and aluminum and maybe 90% of the copper. But that's still not enough. So typically what they would do then is do sulfide precipitation or ion exchange to try to get it all out. This results in significant yield loss, which is losing your economic viability as a business. Looking now for manganese, typically you add some sort of oxidizer to precipitate it out. This can work well in some streams and not in others, but also you're going to have some yield loss of that cobalt, right? You will react with the cobalt, it's not selective, and now you're losing product. On the right side, there's a variety of processes where you can go and make this, we call energy precipitate, the PCAM, cathode active material, directly from the mixture. So then you only have to remove copper and a couple other impurities. You don't have to do this individual separation step like in the left side. But that means copper is even more important. Within there, it will change the structure of that cathode material. It will not have the right purities, so then it will no longer be a battery product. And given that the old battery chemistry tends to be 622, et cetera, 532, that's not conducive to make what we want, which is 811. This high nickel content battery gives the high energy density, high power density materials. So they need to modify the ratios in this mixture to satisfy the conditions to make 811. And in order to do that, they usually have to remove manganese and cobalt. Well, removing the manganese is very tough in these solutions. Removing cobalt can be done in different ways, but you have to do this adjustment. And so we'll get into those specifics a little bit later on. Next slide, please.
So we are creating or moving, changing the game from copper and manganese being the problem makers for the final LIBs. We are getting value out of it. Is that making a sense, Cameron?
Yes.
Yeah.
Absolutely. Mm-hmm.
So the LIB battery grades do not need these metals in their due course of the production. So currently they are sent as waste. There is no recovery happening. With ElectraMet, we are changing the entire perspective from copper and manganese becoming the nuisance metals, now will be becoming valuable metals getting recovered from the stream.
Yes. And when economics are tight in a competitive market, copper is increasing in value. So that is now extra value you can gain for your operational expenses. Yes. Mm-hmm. Next slide, please. So we're going to a little bit of the existing methods and really kind of dive into why they might work for mining industry, but not for this. Except for copper, the standard process is chemical precipitation. So I'm showing here is a sort of solubility curve of the different metals versus the pH. Because adding sodium hydroxide and doing metal hydroxide precipitation works very well for environmental compliance on a lot of wastewater. The problem is, as you can see, every metal here is going to come out. So if you have to get copper out, you're looking at between pH 6 and 8 to get it all out to purity levels. But also you see these are the curves of nickel and cobalt are also not soluble. So it's not selective. It's going to get all those metals out. So what I've looked at, if you go forward one step, this is looking at sulfide precipitation. Can you advance one slide, please? Now, when you do sulfide as the chemical, the solubility curves shift. So if you look now down the bottom left, that little pink line, that's copper. So you can get copper out very well to very low concentrations, but it has to be very, very acidic. The problem there is sulfide plus acid makes hydrogen sulfide gas, which is very, very toxic. So the safety concerns are really not conducive for a lot of facilities. And if you get a little more alkaline, even a pH 2 to 4, you now see all the nickel come off, all the cobalt come off in those, mainly that blue line. So now you're losing all of your products. Advance one slide, please. And similarly, if you look at ion exchange for copper, so this is an example taken from some mining facility where they're looking at to remove copper from some cobalt. And this only has dilute amounts of cobalt, and they have to do about 200 bed volumes before you stop taking cobalt out. What's happening is the ion exchange is not selective enough. It's pulling all the cobalt out with the copper and every other metal. And then after a while, it slowly equilibrates and only takes out copper. So you're essentially saturating and using up 50% plus of your capacity on metals you don't want. And once you get to the black mass leachate, where you're going to have 30,000, 40,000 ppm cobalt, not 30, it's going to even be worse. It's going to exacerbate. So you have to spend half of your processing time just preparing the ion exchange resin to be able to be used for copper. And this also introduces a very high risk of yield loss of that cobalt if you don't do the exchange properly, if you don't have the right regen, if you don't recover the cobalt from that regen solution. So while it may work to get to the purity, it is just too much yield loss, and the operational burden from a labor and a process flow standpoint, and also a footprint, is just not really viable in our view. Next slide, please. And here's just kind of, again, showing you a little more example of the yield loss from precipitation. This is some data pulled out from a German research institute, showing real data that nickel and cobalt will come out if you use chemical precipitation. But the ion exchange is just massive, right? The capacity for these copper selective resins is not big enough. So you end up having half of your plant is now ion exchange just for a polishing process instead of doing a production. And every time you do a regen, every time you expose it to these different metals or any kind of peroxide, any kind of strong oxidizing acid, it's going to break down that resin. So now you don't know what the capacity actually is, so you have to over-design, oversize these resin beds to make sure they are functioning. And it is a massively burdensome process. Next slide, please. And so here is a full flow sheet of example of, this is actually designed by Solvay using their solvent extraction process. You can see they do a bunch of different steps. Usually a solvent extraction to kind of pull away the bulk of one metal, and then a polishing step. And then another solvent extraction to pull away the bulk of the metal, and then a polishing step. And so what we're seeing here is, even through their impurity removal process, there's still too high levels of copper and manganese in these different product streams. So from the very beginning, copper is a big problem. The solvent extraction, the chemical precipitations are not hitting purity requirements, which is going to be 1 to 2 ppm max on these product streams. And if you look at here, right after step 1, that impurity SX, the D2 EHPA, call it DEPA, is usually very good at bringing out bulk manganese. And it's good at bringing out trace metals, but it's still not good enough, right? It gets 95% of the impurities out, but you need 99.99% of those impurities out. So what that does is those small impurities are then transferred downstream to each of these other individual steps. where they now may be even more difficult to remove from that product stream versus if we could do it earlier. So the cobalt SX, the Sinex 272, is the most common process in all the facilities trying to recover cobalt. And it is very good at sucking up manganese. So you can see that bottom right table there, there's still a significant amount of manganese in that product stream. The challenge now is that's a product. They want that cobalt product. So how do they get that without adding new chemicals to it? All right, so if you have to do any kind of pH adjustment, add chemicals, you're now adding more impurities into your product stream. So then you have to then add the chemicals in there to get manganese out, and then do further downstream processing to remove the impurities just added. So it's all increased cost, it all increases the plant size, and it increases the operational burden. Next slide, please. Okay, so that was making all the different metal salts. So here's an example flow sheet of going straight to that, cathode active material process. It looks very similar, right? You still have the copper removal and impurity removal. The only difference is instead of making, a solvent extraction step for cobalt, a different one for nickel, a different one for lithium, they're now taking that sort of purified leachate once you remove the copper and trying to make the cathode material directly from there. So you do chemistry on this, what's called an NMC solution. You add in a variety of chemicals, and it produces your cathode active material process. Again, challenge here, it has to be very, very pure.
So Cameron, with ElectraMet, can you just throw some light? Which of these steps can be totally, eliminated? Like you don't have to do, a series of different chemical additions for the bulk removal, for the polishing, right? We have got, a family of reactors starting from alpha, beta, and delta that can do the job.
Yeah, I think it's more of not necessarily removing process steps. Is that these process steps won't actually work at scale because they haven't built plants yet. So look here on the residual impurity removal IX, that is what we would replace. And we would be much more sustainable, much more reliable, and efficient to actually hit the purity requirements in a smaller footprint.
Okay.
You can potentially take the upstream processes. If you look at the copper SX or the impurity removal, you could use less energy there and not be as you don't have to hit the removal contents then because we can do it downstream. So it's more of mixing and matching what is the right flow sheet for what they want to do. And the ElectraMet system is really flexible and can tie into really any flow sheet, and we can help you optimize, how can you, again, maybe use less chemicals up front for the first step of bulk removal, so you don't have to hit purity requirements from that. So it's all about optimizing the flow sheet and finding what's the best solution at the right operations. Next slide, please. So here's giving some real world examples of this black mass leachate for these two different streams. So the one on the left is a client that wants to make the cathode active material directly. So they have the mixture of their nickel, manganese, and cobalt. They don't want to lose any of that. They just want the copper out. So we're flowing this really black mass leachate through our system, and as soon as we turn it on, you can see the copper comes down, and we're hitting the specifications of less than 2 parts per million. And we don't touch the cobalt, the nickel, or the manganese, so that their product is in the right ratio. They're good to go. All right, using a single pass operation, very high efficiencies. So that means all the energy going into our system is being used to remove the copper and not other parasitic reactions. And on the right, this was a sample from a client who has the final cobalt SX product stream, right? They want to sell this, but the manganese was too high. So traditionally they would add what's called Caro's acid, so sulfuric acid, peroxide, other chemicals to force oxidation of manganese and precipitate it as NNO2. By doing that, you are now going to input stuff into your product stream. You usually have to adjust the pH as well. So all these factors result in the yield loss of that cobalt, and also adds on more processing steps, which increases the cost of hitting that high purity battery grade cobalt. Just like copper, we put this through our system, and in a single pass operation, we are converting that dissolved manganese 2+ sulfate into manganese dioxide in our cell without adding anything else back into that cobalt stream. So we don't need any pH adjustments. We just need solids to not be in there if you don't want to clog, which they don't want in there anyways because that's the product stream. So you have two very viable, highly efficient economic solutions depending on which route you want to go, from straight to cathode active material, or if you want to make the different battery salts. ElectraMet systems can integrate in each one of those processes. Next slide, please. And here's some kind of a little extra flavor. If you look at these solvent extractions, right, they do solvent extraction to remove manganese impurity, but that will bring over some nickel and cobalt. So that's typically a yield loss that you're stuck with. And at a big plant, this can be a significant amount of these metals, and it's a lot of lost value. So we had one client ask us to, hey, we have this manganese solvent extraction that contains 1,000 ppm of nickel and cobalt. Can you remove the manganese and give us a purified cobalt stream? So that's what we were able to do here. Even though you had a small amount of nickel and cobalt, through our electrochemical process, we're able to get that manganese down to purity specifications. So they now have a second stream of a high purity nickel cobalt process they can then recover instead of having to sludge out and send to a smelter. And then looking at the right side, so this is when the customer who wants to make the cathode active material, but the ratio of nickel to manganese to cobalt isn't conducive to make the high value battery material. So they need to remove part of the nickel to have it sort of match with the cobalt, so we can make this high nickel, low manganese cobalt solution. So our solution is able to very selectively tune the manganese concentration in that NMC leach shape, so that once the ratio is set, they can make their cathode active material and have their valuable product. Next slide, please. So here's sort of the breadth of our systems, give you an idea of what it looks like, the footprint, the power requirements, and the handling capacities. This system on the left here is a 16 cartridge modular skid. So each cartridge is operating in parallel to hit higher throughput, higher capacities. The energy consumption we're shown here is it is running at max capacity all the time. That's what we're going to see in terms of energy consumption. It is rare that we ever operate at max capacity. It's going to fluctuate up and down depending on incoming feed process. And the handling capacity is also going to fluctuate based on what is the concentration of the metal and what is the flow of the stream. So we operate more on a metal flux process. How many pounds per day are you processing through how many modules? So we will optimize that design engineering to best fit the process. And on the right, we see our recovery systems that you just put your power in and you're pulling out copper tubes, very high purity. That is pretty standard. It's very modular. If you have more metals to recover, we add on more of these reactors and get higher throughput. But the key piece here is a very, very small footprint for high throughput systems. If we take that skid on the left, and if you want to compare that to what the equivalent ion exchange would have to do for copper processing, we have this, a few meter long skid. If you're on an IX system, you probably have, 500 to 1,000 square feet minimum of space required to fit in that process. Next slide, please. And one of the key advantages of using ElectraMet in our electrochemical system is that it has an innate built-in remote operation, remote monitoring, IoT, analytics, and diagnostic system. So it's very easy to tie into any existing SCADA system and operate from anywhere. So the labor requirements, the operating requirements are very minimal, which reduces the cost. More importantly, because of this IoT built in, we can track everything from pressure drops, voltage, current response, the health of the system. It can tell you exactly how well it's working and preemptively warn you if there's something wrong with the process either in our system or something upstream. So it provides a more holistic approach, a more sophisticated, updated process that can help achieve maximum yield and maximum profits. Next slide, please. And so how we like to proceed is pretty typically when you get a sample of the water, the wastewater or the leachate water, understand what's in there and understand what the goals are, and we'll usually process it in our lab to understand what kind of operating parameters do we need, what kind of flow rate, what kind of voltages, residence time, etc. Once that is done, we can do an on-site pilot to get more of a long-term operational data, and this will basically give us the design specs for a full commercial implementation. Now, given our expertise in these two industries, there is a very likely possibility we can circumvent steps 1 and 2 and go right to number 3. Or we can skip number 1 and go right to number 2. It really depends on the design goals of the client, the size of the process stream. If it's a very large flow, 100 gallons per minute, etc., you usually want to have some kind of pilot process in to tune in on the right design specifications. But in terms of understanding the water chemistries and getting a feasible solution, we're pretty good. We can usually avoid step 1. Next slide, please. And so I hope that helped to educate everyone on these two different processes. And while they may be very different, it's still the same general water treatment solutions being applied, right? Pre-treatment, solids handling, metal removal, post-treatment, recovery, water reuse, etc. And so now I'll hand it back to Jianqi and her team to help facilitate the Q&A section.
Thanks, Cameron, for the wonderful presentation and taking us deep into the, the various or setting the tone what is currently happening in terms of the LIB recycling process as well as the semicon wastewater. So we can take up a few questions. I could see a few questions in the chat box. I could see from Sagar. Okay. So we wanted to have the regulatory norm for UPW water. I think it is more a process dictated term, Mr. Sagar. Each and every process in the semicon loop has gotten, when it is in wet cleaning or it is the initial cleaning, the process dictates the need and the conductivity for the UPW water, if I'm correct. Then there is a question: chemicals required for neutralization and precipitation. So is it for the process? If Cameron can help, or is it for the wastewater?
For the post-processing after our system, right? If you have to neutralize the wastewater stream to meet a pH requirement, this is just sodium hydroxide or calcium oxide. That's something MWTS would be very efficient at. If there's other impurities that we're not targeting, there's other different constituents, then that's going to be very case-by-case basis of what needs to be done. But typically, it's just pH adjustment. And all the semicon facility is just acid neutralization. So sodium hydroxide, calcium oxide, whatever works best for that process.
So to take on his question on the fluoride removal, it entirely depends upon how much of fluoride are we aiming to remove and to what extent. So there could be a different removal perspective for the bulk fluoride, but when it comes to reaching the compliances or removal of fluoride from very low ppm levels to meet the compliance, we have a different technology. So it purely depends on how much fluoride that we are aiming at and what is the volume that we are talking about. So we can curate a solution which could be a two-phased solution, one in the bulk removal followed by the finer removal to meet the compliance or to meet the downstream water recovery units like your RO systems. So we can provide that when we have the data on how much is the fluoride that we are targeting upon. I hope that answers you, Mr. Sagar. So we also roll out a feedback form in the chat box. So the industries or the practitioners who are there with any of these streams who are willing or interested and ready for an pilot validation can express their interest so that we can arrange or to make the necessary arrangements for a benchtop pilot validation in here in India. So we are in the process ourselves and ElectraMet are coordinating things so that we can do a round of pilot validations before we go for the commercial implementations. So you can express your interest that if you are ready with certain streams that you want to actually test with, and probably like Cameron was explaining, there are more than 10 or somewhere 12 flow sheets which are globally used. Probably one of means your flow sheet could be one of them early means studied earlier by ElectraMet so that they could skip one, the step number one and recommend to go for an on-site pilot validation to get the longer design parameters. But if there is something that you have modified from the universally adapted processes, probably we'll need feasibility testing. So it entirely depends upon what means how the process is done at your facility and what exactly you want to alter in that. Yes, Mr. Ashish, you had a question? Yes. You can feel free to post your questions, even after the session. We leave our mail IDs to you. You can, drop us an email. We'll be happy to reply you, and we'll make some kind of a material that gets, shared post the session for the benefit of the attendees to, relook on whatever we have discussed so far. So any live questions?
It looks like there's a question in the chat from Sunny about liquid waste from lithium-ion battery recycling and how that's typically treated.
Yeah, so typically the last step that is the waste is going to be a very concentrated sodium sulfate solution, global salt, and it's typically processed by crystallization, and then you have a significant amount of sodium sulfate byproduct to either try to find an off-taker or you usually dispose down a well. Another solution that is being investigated is to try to take electrolysis reactors and turn these sodium sulfate solutions back into sulfuric acid and sodium hydroxide. But there's typically very, very little actual wastewater or waste in these processes if they're designed properly. Because everything in there is potentially a valuable product.
So I see Mohammed asking, what do you propose when the etching is done by HF and HNO3, probably in the semicon waste? Does that change our perspective? The change of the etching solvent, does it really impact our solution, Cameron?
The only thing we don't want going into our system is hydrofluoric acid.
Okay.
So that would have to be removed upstream.
Okay.
And plenty of solutions for that. But yeah, other nitric acid, sulfuric acid, hydrochloric acid, persulfates, peroxides, any really oxidizer and acid outside of hydrofluoric acid doesn't make a significant impact on the solution needs.
Yeah, and that is standard across microelectronics and other industries where HF is a very, very aggressive chemistry and is usually remediated before any type of treatment or purification process. There's a question, Cameron, from Naveen about extracting each and every element from wastewater or only specific elements, mixed metal streams.
Yeah, we do have the ability to target a number of metals. I don't think we have a slide on that. But we can do copper, silver, gold, manganese, The PGMs, so platinum, palladium, you can do some tin, lead. Really, if you can do any kind of electroplating, electro-oxidizing, we can get it. Ones we don't really target are things like zinc. Nickel, cobalt are going to be very case-by-case basis. But typically anything on that sort of transition metal block on a periodic table is most likely targetable. Things like selenium, arsenic are a no-go. Most of the metalloids and non-metals are probably a no, but possible. But usually right in those triads: silver, copper, gold, silver, the PGMs, manganese, tin, lead are sort of the sweet spots for us. But if you have one we didn't list, we would be interested in learning more and taking a crack at it.
Yeah, Cameron, I posted a mixed metals approach. Can you talk a little bit about what it shows? Basically, is kind of the different voltage potentials. So it shows the cartridges, and then kind of just the escalating voltage that may help with that conversation.
I see it. Yeah, so we use what's called the electrochemical series. Essentially, every metal has a voltage you need to turn it from dissolved into metal. And we will put these cartridges in series and get the lowest one first. For example, we can get silver out at a very low voltage, so that will come out first. Then the next one can do copper at a slightly higher voltage. Then we do things like cadmium, tin, lead at higher voltages. And then you start getting to this range where you're about the same voltage to make hydrogen gas, which is why it gets very finicky with nickel and cobalt. So you have to have very precise water chemistry and operational parameters to get the nickel and cobalt out at these higher voltages. Things like PGMs are going to be very, very low voltages, even lower than silver. The ones like manganese, that comes out in a different reactor design, but it's still pretty low voltages. So we can basically just on operational voltage, we can line these up and design these to target what metals you want. So it's just like dialing a knob on each one, setting 1, setting 2, setting 3. No process changes required.
Any more questions that we can take live? If there are no live questions, I think we can conclude the webinar. Thanks, Cameron. Thanks, Mike, for joining. It is a pretty early for you from joining, and I thank all the attendees because it's usually not time for them to stay back and take part in the webinar. We hope and look forward for more interactions from the registered attendees and the attendees here, so that we can discuss on the holistic solution that can be delivered. And as I said earlier, if we are ready with ready for the pilots, you can express your interest so that we can compile, and we can do for the on-site pilots, and we can also review your flow processes and recommend or our solutions that can best get fitted into the flow process, so that you can see the benefits, the value deliverable that is getting added for the entire flow process. So we are open for the discussions on that. Thank you all. So as we draw the curtains today, please send us the forms filled, so that we have data to come back to you. And we also will share this information with the ElectraMet team over there, so that they can also refine any kind of solutions they can be. The best part of ElectraMet and the entire solution is it is more expandable. So it comes in as your facilities are getting expand phase wise, our solutions can also be delivered phase wise. You don't have to make the entire the capital investment upfront. So how you progress in your the factories or the production setup, we can match your progress. So it is entirely expandable, and we can match your face there. So thanks everyone who had participated here. Thanks Cameron once again, and Mike for joining. Thanks Mohammed for supporting the entire webinar campaign.